Welcome back, my good friends. In the last video, I started going through this equation sheet for a university level electromagnetism course, specifically the magnetism section. I did a video before that on the electrostatics version, and you guys can see here, I went fully into the lo-fi theme. I know most of you guys are watching this kind of late at night, so I want it to be easy on your eyes. So I hope this looks good and there's no quality errors. So in the previous video, like I said, I went over this big block over here of equations related to magnetic field and force. We also took a mini pseudo break to talk about constants and some of these little helpful equations down here. And we ended off with kind of a half-assed version or follow through of this, which is going to bring me to the start of this video. I have some redactions or corrections or just further information to share with y'all related to this section here. If you remember, I left this equation over here and this equation over here for you guys to take a look at on your own because I did not really have a solution or answer or anything to tell you about this. So today I'm going to start off by talking a little bit about this equation. This guy over here, I'll just say something very quickly right now about it. And when we cover these two, we will go into the AC circuits, which is going to be the bulk of this video. Yeah, and I'll go through a nice slow review of this because these equations look a little spooky. And honestly, I don't really feel like doing this over here. Maybe we'll spend like a quick 5 or 10 minutes on that. So I hope you guys enjoy this 77-hour long video. Let's get right into it with this guy over here. This here is the energy density created by a magnetic field of strength B. So you plug in B squared, divide by 2 mu naught, and you get energy density. I haven't seen any problems with this. Apparently, it's also equivalent to potential energy divided by electric potential. So I'm just going to spew that out there. If you want to see a problem related to this, just Google search energy density undergraduate electromagnetism problems. Take a look at that. The main thing I wanted to cover is this here because I thought this equation, the way you derive it and what it means is actually very cool. So we're going to start off with that, and I'm going to write that equation over here. So we have delta V equals, I think here it was an EL. Is that correct, or is it ED? EL. And then we get BLV. Okay, so just looking at this, we know that this here is electric potential. This here, well, this is the E field, and this is the B field. And this over here is velocity. So if we just take this chunk of equations right here, I'm going to write that down over here. We got EL equals BLV. You can see L here is the same thing, the length. I haven't really talked about that yet. But if you cancel these guys, you get E is equal to BV. And if you solve for V over here, you get the equation that we calculated in the velocity selector. So pretty interesting how this random thing over here connects to the section where I was talking about the velocity selector. And if you saw that part of the video, you'll remember that how I calculated it was I took this equation for the force due to a magnetic field and I equated it to this equation, the force due to the electric field. So I equated these two, and from that we also got this equation here. Velocity is equal to E over B. So I'm just sharing that with you guys here. But let's actually take a further analysis view of what this equation is telling you. I'll explain to you guys right now what it is. So if you imagine an electric field, or sorry, a magnetic field like this going into the page, and you imagine a conductor of length L chilling in this magnetic field. So this is L, right here. If we move this guy with a velocity v inside this magnetic field, which has a magnitude b, and the magnetic field is pointing into the page, you guys learned from the first section here that a charge moving with a velocity v in a magnetic field b feels the magnetic force F. You also learned in this section that there is a magnetic force that is felt by a wire if the wire with current I and the length L is placed in a magnetic field B. So due to the charges in this current, the charges are moving, they feel a force due to this magnetic field. So keep those things in mind, but let's say now we just have a wire here with a bunch of electrons in it. So all these electrons are just chilling in the wire. And we take this whole wire and we move it, let's grab this too. We move this whole thing, boom, through the magnetic field with a velocity v. So when this happens, you have to take a deeper dive into this wire. Let's say we zoom into this wire and we're looking at all the electrons chilling in here. Right? Let's say the wire is made of metal. The metal has electrons in it. It's a conductor. And we are moving pretty much all of these electrons with a velocity v this way. And since the entire region here feels a magnetic field into the page, you can do that v cross b to find the force. So we have this thing, which is the first equation in this equation sheet. We have q, which in this case is the charge of the electron. Sometimes it's written like this with a minus sign to remind you guys that it's negative. And we have here v cross b. So using the right hand rule, I can point my thumb in the direction of v, my pointer finger in the direction of b, which is down into the page, if you're looking at this screen on a flat table. And then fb, this guy right here, I'm going to draw it in orange, is going to be going upwards. But remember, we have this electron, which is a negative charge. It's negative 1.6 times 10 to the whatever, like some number here, coulombs. This negative, if you check my vector video, will take this vector here, the vector we get from the cross product, and flip that boy 180 degrees. So the force that the electrons feel is actually not going to be this guy. It's going to be this guy here. So I'm going to just quickly erase this, boom, and just draw this vector down here. So this is the force due to the magnetic field and this velocity here of each of these electrons. So, okay, what have I said here? All of these electrons will go down here and they'll like start pooling up over here. Does that make sense? So if the electrons all pool up down here, they will start creating a negative region on this side of the rod, which would leave a positive region on this side of the rod. So what we get here is actually a potential difference, delta V. If you remember, that's straight up what a potential difference is. If we attach both sides of these to some kind of load, like a light bulb, we can get it to glow. So this delta V is straight up what the equation is telling you. Delta V equals BLV. This equation here, the first one, the one that you see over here, right? And you might be asking yourself, why is this EL over here? Recall that this thing here was a concept we talked about earlier in the course. I actually did a video introducing the electric potential, so take a look at that. But this equation here was one specific equation that we developed in that section, and it is straight up the potential difference between capacitor plates, or the potential difference of a constant, uniform, unidirectional electric field. So the electric field comes down like this. That's the E field. It has one direction and an equal strength everywhere, which is what happens in capacitor plates. And we have a distance over here, this distance, or you can call this L, length, distance, same thing. And then here you develop that potential difference. And also, depending on if you choose this as point A and this is point B, remember that potential difference is normally this, or if you flip them, you spit out a minus sign. So depending on your perspective, whichever location you label as A and B, you will get either a negative sign here, or how this equation was written, you will not have a negative sign. You'll just have EL like this, positive sign. So basically, we have a rod, a electric conductor with electrons inside of it. It has a length L and it's moving with a velocity V inside a uniform magnetic field. The magnetic field is perpendicular to the velocity. So through that right-hand rule and the force equation, you develop this equation, and you can see that there's a potential difference developed here between the ends of this conductor. So attaching a circuit to this will give you a voltage which produces a current. So I actually want to let you guys know about these two YouTube videos here. Peep this one, Stewart Physics, Moving Conductor, Magnetic Field, V equals BLV. There's a bit of different notation here. This guy does B cross V instead of V cross B, but he starts off from this base principle and like derives this equation here through kind of the same sort of stuff I was talking about. So peep this guy, check some of his other videos as well. They might be useful. And also take a look at this video here by Physics Ninja, Motional ENF. The beginning of this video basically talks about the same exact thing, a conductor that's moving with a velocity V. It gets an EMF, right? This EMF is derived here. And he also solves this problem with a circuit here with this bar moving back and forth. So you can solve these problems. Normally there's a resistor here and they ask you for the EMF and the current and force and stuff like that. So this is a circuit and this is kind of analyzed on its own. The way I took a look at this problem normally was with Faraday's law. So Faraday's law was this induced EMF is the change in time with the change of the magnetic flux with respect to time. And there's a negative sign here because of Lenz's law. So take a look at this video. This guy actually analyzes this problem with by just looking at the original conductor, and then he solves this problem also with Faraday's law. So peep this, peep also some of his other videos, probably going to be pretty helpful for this exam. But now let's head back to the equation sheet. That was basically me going over this equation here, useful for when you're doing stuff related to circuits. I also didn't really talk about this or these equations too much, but I think that'll be a nice segue into these AC circuits. So I'm gonna talk to you guys about circuits. Let's start right here. Basically, all you need to know about circuitry is this. Ohm's law, we have V equals IR. All right, so you may have seen this before, but in case you haven't, I will tell you what each component means. This is a voltage or potential difference or electromotive force. Now there's multiple ways of looking at it, but you could just think about it as voltage. This I represents current, and this R over here is resistance. So you can see this equation looks fairly similar to the standard line, y equals mx plus b. In this case, b is equal to 0, right? This equals 0. M is the resistance. We can plot I on the x-axis, and we can plot voltage as a function of I on the y-axis. So if you plot a graph like this, we put current here, and we want to observe, what the current does as a function of time. So let's say we have a circuit right here with a resistance and a voltage. This is the resistor R. Ohm's law basically tells you that the voltage or the current increases in a straight line as you increase the voltage. So I increase the voltage a little bit by one unit length, like let's say I jump up to 1 volt here, then the current jumps up to some amount. What is this amount? Where you get it from straight up the equation. V equals, let me actually write it in y equals mx plus b form. R times I. So if you have the resistor, you can do some algebra here and calculate what current this would be. But you could see the same thing happens if I increase to 2, then I also increase the current through this resistor. Okay, so that is an important thing to know, Ohm's law. And normally this happens in like DC circuits. So DC is when you have voltage here over time, and the voltage just stays one value, like let's say 6 volts. This is like the voltage produced by one of those batteries that look like this. You attach something here, and this gives you a DC supply. But you can also take a look at alternating current, which is what we're going to look at right now. So for alternating current, the voltage as a function of time does something differently. So before I plotted Ohm's law, right, I had current and voltage over here, voltage as a function. Here I should have put I. Voltage as a function of current. So as I'm changing the current, what happens to the voltage? Or as I change the voltage, what happens to the current? You can kind of interchange the two. You'll see most of the time in these circuit problems, they ask you what is the voltage or what is the current, or in a special kind of problem, they tell you, oh, we have a power supply of this many volts and we figure out there's some current running through it. What would be the resistance of our load? Stuff like that. So here I plotted an IV graph, current on the x-axis, voltage on the y. Here I'm plotting voltage as a function of time. So as time moves forward, what does the voltage look like? For a DC circuit, DC, this is direct current, or you could say direct voltage, but most people use direct current. You can see the voltage stays the same value, let's say like 6 volts, and it stays the same. There's no changes or anything. If you turn the battery off, maybe it'll drop like this, but there's no oscillations or anything like that. This is different from AC voltage or AC circuits. This is AC, alternating current or voltage. In this case, I'm plotting the voltage. So AC/DC is just like, what we've come to name these guys. And you can see the voltage here increases. So at time equals 0, the voltage is at 0. And then as time moves up, the voltage increases to a maximum value. We can call this V max. And then it starts decaying until it reaches 0 again. So after some time here, whatever amount of time here this is, the voltage does this little loop and then it goes back to 0. But then it keeps going to a negative voltage. Remember, potential can be positive or negative. Here it reaches the same kind of V max, but on the negative side. And then the plot just repeats itself. So we've actually found a equation for this specific function. This, you could write it as a sine wave. And what you put inside the sine is this omega times t. And over here, the amplitude, you can put V max. So this is one specific function that can produce a AC voltage. There could be many other functions. So right here, I've actually plotted the exact sine function. And here you can see I can change the amplitude all the way up to 10. And it actually reaches the value 10 right there, you see. And I can also decrease it to, negative 10. Let's see what happens at 0. At 0, you could see that the sine function becomes a flat line intersecting y equals 0. And as I increase it, let's just drop it at 5 over here. You could see the maximum value here is 5 and the minimum value is negative 5. Cool. And I can change the axis like that so you guys can see. And if I change W, the little omega that's being multiplied by the x, notice that now I changed V to Y and T to X. So the time is on the x-axis, the voltage is on the y-axis. I can also change this W, which is the omega, and you'll see the function gets squashed. Or it could be, well, up to 0, it gets really, really flat, similar to how it was when A, the amplitude, was 0. And as I increase this W, you can see the sine waves get kind of squashed. So you see more of them in one little unit block. Take a look, for example, right here from 0 to 5 on the x-axis. You could see 1, 2, 3, 4, 5, 6, 7, 8, about 8 peaks when I have omega 10. If I change omega to 5, let's change it exactly to 5. We have between 0 and 5 on the x-axis, we have 1, 2, 3, 4, about 4 peaks. And if you change this to 3, we have maybe 1, 2, 3 peaks. 2, we have about 2 peaks. 1, we have exactly 1 peak. So the omega is telling you how fast this wave is oscillating back and forth. In circuitry, it's called the angular. Actually, is it the angular? It's the frequency of oscillation of the voltage. So you plug this into your wall. Most of the planet has the omega here, the frequency, as like 50 hertz, which is 50 oscillations per second. So imagine this omega, instead of 10, I increase this to 50. So just for 1 second, 1 unit on the x-axis, this sine wave goes up and down 50 times, which is crazy. Okay, I just want to show you guys this here so you can kind of see the effects of this and what this function here looks like. Okay, cool. Now, the main principle of AC circuits is we have a resistor here, and we want to figure out, okay, if we apply a voltage, which we will say is Vmax, this is the amplitude, and then this is the waveform of the voltage. What happens if we apply this voltage to a resistor? Does the current look like anything? Well, remember Ohm's law. We have this guy here. If we plug in V is equal to this over here, so we have Vmax. Vmax is just a constant. It's like A. Like you could set Vmax to 10, and then the sine wave would oscillate from positive 10 to negative 10. Here we have sine. Here we have omega, which I haven't specified yet. I mean, I also haven't specified Vmax yet, but anywho, we have this, and then let's rewrite the rest of the equation, IR. Cool. Now, if we are given R, so R is equal to like 10 ohms, for example, normally R is given to you because you can create a circuit and you can buy a resistor with a certain amount of ohms. We can divide this guy over here and get an equation for I. Are y'all okay with this? So if we have this, we can kind of simplify it a bit. Like here, what I'm looking at is a function, and then it's being multiplied by this Vmax, which is a constant. And the whole thing is also being divided by a constant. So I'm going to group up these constants together, and I will get Vmax over R times this same function over here equals I. And now I can actually put I of t, because I can see that, let me actually delete these guys. Yeah, make sure to take a look at this video and the other one. I think these will be very helpful. Shout out to my boys, the physics community. So yeah, as I was saying, we have a function here for the current running through a resistor, and you can see it actually behaves very similarly to the voltage. The current also has a sine omega t. So just like how the voltage is going up and down like this, you apply an oscillating voltage. The current, if I plot over here, like I'll plot the voltage as a function of time on this, the current will also follow the same sine wave. It has the same omega, but it has a smaller amplitude. So I'm going to try to draw this a bit nicely here. And these peaks over here, so this red peak will be Vmax. Same thing on the negative side. This would be negative Vmax, same number. But the blue peak will actually be a different thing. It will be I max, the maximum current. And this I can plot as I as a function of t. we straight up have these values. So this one is Vmax sine omega t, and this one here is Imax sine omega t. And the reason I'm drawing Imax less than Vmax is because we actually defined what Imax is when we solved for this equation using Ohm's law. This is Imax. You see that? Imax. And how do I know this? Go back to Ohm's law. Remember this equation? This is literally going to be helpful with the entire equation sheet. Just remember Ohm's law. And you'll see here we have Vmax over some resistance is equal to Imax. If I move this back to here, well, I mean, that's straight up what we used in the first place. We used this, developed this, we got this, and then I replaced this thing with Imax. So if I have Vmax and divided by R, let's say R is equal to 2 ohms, or, interesting. So if R is bigger than V, like let's say V is equal to 1 volt, and we divide by 2 ohms, then Imax will be 0.5 amps, right? But if we divide by a smaller number, like we have 2 volts divided by 0.5, what is this, 4? This would be 4 amps. Okay, so the reason I drew this Imax below here is because I'm assuming the resistance is smaller than the voltage. If the resistance was bigger, then the Imax would go all the way up here. Right? So you have to take a look at these guys, and you have to remember Ohm's law, and from there I think you should be boolean. This is Vmax over R. And just keep in mind that these sine waves are the same. So keep that in mind. Now let's go back very quickly to the equation sheet and just take a look at what we're seeing here. We have this stuff here, which I will, these equations, perhaps I will go over them, but like I said, check my first electrostatics equation sheet video. I go over this stuff for the RC circuit. For the LR circuit, or LC circuits, in this case I think it's LR, it's kind of similar behavior. The reason I'm introducing Ohm's law is to kind of help you guys with this section. So you can see a lot of weird symbols. We have phi, XL, we got this omega here, a Z, some weird stuff, but look at most of the equations and keep in mind Ohm's law, okay? And keep in mind that this is voltage, this is resistance, this is current. If you have that in mind, then forget these top equations just for a second. I mean, maybe you can see here R, like that looks like resistance, resistance, but forget about these top equations for a second. Take a look at this one. This is lowercase I subscript C. This means current. So this equation is for the current subscript C of a capacitor. And you can see here we got omega C. Don't worry about that for now. Don't stress. We got delta V max. This is a voltage. And here we have that sine function. Okay, so just keep in mind this equation and keep in mind that you know these symbols here. And I'm slowly introducing you guys to this sine function. So, okay, cool. That's the first equation. We have this one here, which is Q equals C delta V max sine theta. Okay. No need to stress. If you remember the first equation sheet here, when you guys learned about capacitors, you learn about this equation over here. Capacitor. The capacitance is defined as the charge on the capacitor plates divided by the potential difference on the capacitor. If you multiply this V here, you get the classic equation Q is equal to CV for a capacitor. That is, we're going to use that quite a bit. Q is equal to CV, and that's the same thing used over here. Take a look at this. Q is equal to C delta V, and then they have this little sine term because we're in AC circuits. Okay, so this equation is also nothing new to you. And this equation also, I want you to think about it as nothing new. It's just Ohm's law. So either here you go back to Ohm's law, or you go back to the original equation sheet, which I have a video on. So I'll go into these equations a bit more deeply, but just a big overview to kind of show you guys that you already know most of this stuff. If you've followed along with the series, or if you've had a general introduction to circuits. Here we see a couple of similar looking equations. Delta V, delta V, delta V. They each have a different subscript, CRL. And again, think of Ohm's law. So this is literally telling you voltage, voltage, voltage of capacitor, resistor, inductor. And over here, they got an equal sign. Again, very similar stuff. They each have an I max here. They're then followed by this different symbol here. So for the capacitor, you have an XC. For the resistor, you just have an R, no XC. For the inductor, you have an X subscript L. So these two look similar. R is a little different, but they each have an I max, and they each have this other thing being multiplied there. So you can think of it I max multiplied by this sign thing. And that's the last thing I want to mention. The final thing in each of these equations here is the sign term, which again, I introduced you guys before. We're going to dive into it a bit deeper and why they look different, but just keep in mind the similarities. And keep in mind, each of these is just telling you what is the voltage, Ohm's law. So we can see for the capacitor, we got a sine function with the same omega t, except there's a minus pi over 2 here. Very important thing. Slightly different from the original one we saw, the sine omega t, which I plotted. So I'm going to plot this one as well and show you guys what the difference is. But let's just move on and see what it is for the resistor. Sine omega t, no pi over 2 anywhere, just the sine omega t, the classic sine omega t, the thing that I introduced to you guys here if we have a voltage supply. So voltage with a sine function, omega t, it follows this path here. And you can see the resistor, it follows the current on the resistor here. I didn't specify that, but in the equation sheet, they actually do specify it. The voltage across the resistor is equal to I max R. And if you just take a look at this, this is also Ohm's law. V equals I R. You have this extra sign thing here, again, because we're in AC circuits, but keep in mind, the resistor does not have this extra pi over 2 factor or phase angle. We'll get to that again in a second. Also, I seemed to have missed this, but the equation doesn't stop here or here or here. They actually give you another way of writing it here, here, and here, and then the semicolon comes. So this stuff here is actually just 3 equations written 2 different ways each. And they are both giving you the voltage on the capacitor, resistor, and inductor. Very useful. If you're asked any question about the voltage on a capacitor, boom, just outline this equation and be like, okay, this must be used somewhere in the AC circuits. So just to kind of quickly take a look at all of the first equations, we just saw that the resistor had this form here. Let's take a look at the inductor. We have, again, an I max, this little x, and again, a sine with the omega t, but this time a plus pi over 2, which is different from the minus pi over 2, which is different from the nothing on the resistor. So keep in mind these differences. And then let's quickly take a look at the second half of the equations. You can see the resistor remains like this. So the resistor, the voltage drop on the resistor, follows the voltage drop on the resistor sine omega t. What does that mean? It's basically telling you this plot that we have here, the voltage, when it's applied to from a power source like this onto a resistor, it creates a voltage difference over here, right? This delta VR. And you can see if you just follow this all the way over here and follow this all the way over here, like it doesn't matter where you put an ohm meter or a voltmeter, if you put it here, or if you put it here, or if you put it here, it measures the same voltage everywhere here. So this VR, delta VR, the voltage drop across this resistor is exactly the same as the voltage drop across this battery. I mean, obviously it would be different if there was other stuff happening here, other circuits with other components. But if you have a simple circuit like this, then that is the equation it follows. And it's good to know that, because then you can break it down more complicated circuits with these equations here. So delta VR is equal to delta VR, the amplitude, times sine omega t. And we're assuming the voltage that we're applying is something like this. So in an AC circuit, I produce this voltage, like this is coming from my power supply, a voltage that follows a sine wave like this. I attach a resistor to it, and the voltage on the resistor looks identical to the voltage from my battery supply. Cool. For the capacitor and the inductor, you actually see a slightly different behavior. Cosine and cosine for the inductor and the capacitor, and the capacitor actually has an extra negative sign, which the inductor doesn't have. So again, little voltage, little voltage, little voltage. What is the voltage amplitude across the capacitor. What is the voltage amplitude across the capacitor? Well, if you apply a voltage source that looks like this, then the voltage across the resistor would look the very same. The voltage across the capacitor would look slightly different, like a cosine with a minus sign in front of it. And the voltage across the inductor would look also a little different with a cosine. Okay, I'm going to plot these and we're going to get a little deeper into where they're even coming from. But I just want you guys to see that this section is literally just Ohm's law. Just remember Ohm's law. Again, you know, you have to learn some extra stuff like sine functions and cosines, but mainly Ohm's law, and you get through most of the equations. So we went through this equation. We went through this, and this equations, and all we had to know was Ohm's law, and you know, a bit of stuff about like what sine functions look like if they look like this, and this is the amplitude and this is the frequency of oscillation. Also, this equation here you can get the beginning of the equation sheet, the equation that governs a capacitor. Cool. Now let's take a look at, again, I left off these equations here and we kind of just went through this bulk here, but let's complete this by taking a look at this and this, some extra equations here. And again, you guys will see it looks super similar to Ohm's law. We have an I max. We have a delta V max on the other side of the equality. There's an equality here. And it's on the top of a fraction. And on the bottom of a fraction, you have this little Z over here. We saw Z somewhere else over here. Don't worry about it. We'll get to it. And we have an XC, which we also saw somewhere. We saw the XC over here. This is X subscript C. C stands for capacitor. And we also see an X subscript C in other places here too. Actually, they straight give you what X subscript C is here. So again, don't worry about that. I just want you guys to like take a grand overview of the equation sheet. And again, realize that if you have this over here, like, let me write out this equation like so. We have the first equation, this one over here. We got I max, and if I multiply this XC on the other side, we have I max XC equals V, delta V max. This literally looks like V equals IR. I max is right here, V max is the V, and now we have XC as this like resistance. And you might be like, okay, what is this resistance? Like, why are we just changing this letter XC to the resistance? You can think about this as the resistance of the capacitor, or the, sometimes people use the word impedance or reactance. Basically, when you learn about the resistor, you just learn about standard resistance, how it affects voltage and current, Ohm's law, right? But then when you learn about capacitors and inductors, those guys behave a little bit more weirdly. They have transient effects. They move around and change their behavior. They're not as simple as the resistor. They actually depend on the frequency of your AC circuit over here. You can also analyze capacitors and inductors in DC circuits, which we took a look at up here very briefly, but I feel like you know, it's more important to look at these AC circuits. You can apply your, you know, knowings and knowledge onto the DC circuits if you wish. We got a equation here that looks like Ohm's law, very cool. And we have also this equation here that also looks like Ohm's law. So this guy is a little different, I max. Let's again multiply the Z on this side. So we have Z, and we got this delta V max. Again, very similar to Ohm's law, V equals IR, except Z now looks like this R. And here you can see Z actually is defined as, that's these three little lines over here, defined as, and we got a square root R, and we have also these guys. So we'll talk about this equation too, but I want to show you guys how taking a look at these bottom equations and keeping in mind Ohm's law can basically explain to you most of the stuff going on here. And by knowing some of this stuff, you can actually relate it to the first couple equations and piece together that stuff. Okay, so now that we know that, let me erase all of this stuff over here and get back to the main dealings of the equation sheet. So like I said, we went over this guy. We saw how the first equation sheet has this. We went over this guy, and we just went over this little Ohm's law that looks a little different. And we also went over this and this equation. And now we have this over here. Take a look at this equation. We literally have I max, right? We have delta V max. okay? And we have this thing down here. This already looks like Ohm's law. In fact, if you take this equation, which is Z, which is, it gives you this big square root here. This big square root is exactly the same thing as this. Square root r squared plus, and then you have brackets, xl minus xc, and then you square that whole thing, and all of this is under square root. That is straight up given to you. If you take this and replace it with Z over here, you get brought back right to this equation over here. You guys see that? So again, this is literally just Ohm's law. Ohm's law taken from here. Now I'm kind of pushing away from actually talking about this stuff here. And the reason that is because it is a little more complicated. We're going to get into it right now. But I want to show you guys that if you keep in mind the stuff that you learned from the first half of the semester with DC circuits, it applies very nicely to this. And keeping in mind Ohm's law, you'll pretty much, like right now, we covered all of the equations except these top 4 equations. And again, like I said, even if you don't know those top 4 equations, going through this stuff and just kind of looking at similarities between these equations and Ohm's law, it kind of builds for a nice foundation of this stuff right here. Okay. What I'm actually going to do right now is take a moment and straight up derive these equations over here, which means I will derive this, this, and this, and we will show you how you get these equations over here. Once we know all of this, we will kind of understand what XC, R, and XL mean. We're going to derive these equations in the process. And then we're going to, from this, we're going to see how easily this equation, and this equation are built up from that knowledge. Is that okay with you guys? So again, know this stuff over here related to Ohm's law. Understand that we have moving pieces now, like these sine functions, which have the variable time in there, due to AC circuits, alternating current. And from that, we bring into play kind of new things like this XC, XL, this impedance reactance stuff. And we're going to make sense of the entire section of the equation sheet. Okay, so here's the equation sheet, and I'm going to start off with this equation here, right? I'm going to actually outline it in blue, and we're going to derive this. So imagine you have a circuit that is attached to a resistor. This is the resistor, and the voltage supply here is delta V. So what is delta V? Well, in a DC circuit, it could just be 6 volts like a battery, but in an AC circuit, like we showed before, it follows this sine function. So we have sine omega t. This is the frequency. Omega is equal to 2 pi times the frequency. This is the time. And this is the max voltage. All right, and this is the resistance. So if you remember, in the first section of DC circuits, we learned about Kirchhoff's loop rules. I actually forgot how to spell the boy's name, and I don't want to disrespect him, so I'm going to just do Kirchhoff. You basically have 2 rules. The sum across a loop of voltage drops is equal to 0, and the sum in a junction of currents is equal to 0. So if you have a circuit that looks like this, here we have a capacitor, here we have a resistor, and here we have an inductor, and we have this system here, resistor, capacitor, inductor. So I'll actually label these guys. We have resistor, capacitor, inductor, resistor, capacitor, inductor. And this is the voltage source, epsilon. So you can see this here is a series circuit. Each of the elements follows one another and they're connected using one loop. Meanwhile, this here is a parallel setup. So each of the things is parallel here. You have one, the other, and the next, and their ends are attached together. You can see the ends of each of these devices is actually attached together, and they are all attached to the ends of the battery, which is completely different to this. The ends of this guy are not attached directly to the battery. They're attached first to the resistor and then to the inductor. The inductor has one end attached to the battery over here, but its other end is attached to the capacitor. Make sense? In this case, the ends are all of them attached to each other and to the common rail, which is the voltage. But there is junctions here. You see 1, 2, 3, 4 junctions. So there's junctions. There's more junctions and more loops. Here there is 0 junctions and 1 loop. Does that make sense? So what I want you guys to take a look at is if I have a voltmeter, over here, and I attach it here, or I can attach it instead here, or I can attach it here. It's all going to be the same because the battery over here is producing a potential. It sets this side of the wire to that potential. So this is going to be at that potential, this is going to be at that potential, and this is going to be at that potential. And same thing on this side. So wherever you take the voltmeter, you can take the voltmeter, measure this and this. You can measure this and this, or this and this, or this and this, this and this. All of it is going to give you a potential difference of this. That's completely different than this scenario. If I take the voltmeter and measure it here, the voltage that I would get is exactly equal to epsilon, this guy. If I measure this voltage, it will not be equal to epsilon. We don't know what it is, but we can label it VR, okay? And that means that this voltage here, we don't know what it is either, this voltage for the capacitor, but we can label it VC. And this voltage here for the inductor, we also don't know what it is, but we can label it VL. So these voltages are not equal, okay? That is the series circuit. But in the parallel circuit, they are equal. Now that's just for the voltage. Keep in mind the current also changes. The current here flows, but over here it breaks into 2 pathways. So some of the current goes here, some of the current goes here. And then again it breaks into 2 pathways. Some of the current goes here, some of the current goes here. So if I take an ammeter is placed over here to measure the current. If I measure the current here, it will be different than the current here. And that will be also different than the current here. And that might also all be different than the current here. But if you measure the current here in this ammeter, the current flows here, it enters this ammeter, it flows through here, and the current has nowhere to go. So if I take the ammeter and measure the current here, these are for sure equal because the current exits here, goes all the way around, and enters here. There's nowhere else for the current to go. There's no other junctions. Here, there are different junctions. So please just keep that in mind for series and parallel circuits. And for that reason, also keep in mind when you're asked a problem and they're asking you for the voltage here, here, or here, you can use the Kirchhoff loop rules. And the way you set that up is you do, okay, we have delta VR. This is the voltage drop across the capacitor or the resistor. Delta VC, voltage drop across the capacitor. And delta VL, the voltage drop across the inductor. And we have the battery. All of these guys added together gives you 0. This is literally from Kirchhoff's loop thing. In this case, you kind of have to choose one loop, right? This loop or this loop or this loop. And the loop that you can choose will either have just this guy, the battery, and the singular component. So this is the first loop that I chose over here. This loop, you can also apply Kirchhoff's loop rules to it, and it would look like this. This plus voltage drop across the resistor equals 0. That's completely different than this equation here. And they're both obtained from just applying Kirchhoff's loop rules. Again, we can apply another loop, which is the secondary one with the, it's actually the first one with the capacitor, because I wrote the resistor for the second loop here. And this, you can also apply Kirchhoff loop rules. You do this plus the voltage drop across the capacitor equals 0. And from this equation, you can maybe solve some stuff, find whatever. And we can also do the final loop, which is voltage drop across the inductor gives you 0. You can again also apply the junction rule here to find current. So if you want to label the current here, label this current I1, maybe I2. This could maybe be I3. This could be something else. And using Kirchhoff loop rules, you can analyze this circuit as well. In this scenario, you have the same current going in and out of the system. There's no junctions. Okay, so keep in mind that stuff because that's going to be a starting point of how we analyze these circuits, Kirchhoff loop rules. So now that we have that in mind, we can take a look at this circuit here, which is basically one loop or just a simple circuit with a resistor on it. All right, I'm going to erase all this stuff here so that it looks a bit cleaner and we can just analyze this resistor without worries. So, okay, like I said, Kirchhoff loop rule is valid. So we can now apply Kirchhoff loop rule. The voltage drop across the battery and the voltage drop across the resistor combine to give you 0. Does that look cool? Okay, and now what we're looking for is we're looking for delta VR. Again, I want to derive this equation. What I do know is that this thing is given to me. This is the voltage source that I'm applying. So I can actually do V max times sine omega t plus delta VR is equal to 0. Okay. Now if I take this equation and I move delta VR on the other side, I have to subtract it on both sides. So I get minus sine delta VR is equal to V max sine omega t. Let's take a look if that looks fairly similar. No, we actually have delta VR I max R sine omega t. Interesting. And here we have VR sine omega t. Okay, interesting. So in this scenario, you have to take a look at Ohm's law and remember that the circuit here has this voltage, it has a current going through it, and it has a resistance. So you can break apart this Vmax into Imax, the maximum current flowing through the resistor, right? This is literally Ohm's law. This is why this equation is so important. And this is also why this equation is included over here with the Z. We're going to include it a couple more times. We're going to use it a couple more times later on. This minus sign is a bit interesting. Okay, so what I have here is this function here, the red function, which is the voltage supply, and then here we have the same function except with a minus sign in front of it. So you can see they're completely like mirror images, and this is a bit of an incorrection, which is like, remember when you did Kirchhoff loop rules, you had to see the direction of the current flowing, and if the direction of the current is going this way and the loop that you chose was going like this, then this would be minus delta VR. So you would have a minus sign here. This minus sign would take care of this and would take care of this, and it would not have this minus sign here. So there's a couple scenarios like this in physics where there's a pesky minus sign and like you're very close to getting an answer right. Everything is looking good except for that minus sign. In this scenario, guys, I would say don't worry about it too much. If you really want to look at it, take a look at Kirchhoff loop rules and how to do them and where minus signs and stuff come from. You would get rid of this minus sign. But in this case, we're just going to be kind of lazy and do absolute value of this and get rid of this minus sign. So if we get rid of that minus sign, we actually get the same equation as what we are given in the equation sheet. This guy over here. Delta V is equal to Imax R sine omega t. So basically, the voltage across the capacitor looks very similar to the voltage applied to, I maybe said capacitor there, but the voltage here oscillates the same way as the voltage applied. Makes sense. The interesting thing is, what is the current? And in this case, I mean, I kind of showed you guys what the current would look like in this scenario up here. You would just have the same thing in phase. All right, so I'm going to keep that just in mind and try to analyze the circuits that have a capacitor and an inductor to see if we get some similarities from this. Cool. So yeah, just keep this in mind. If you have like a question that says, what is the voltage on a resistor? Pull out this equation. If you have Imax and R, use this. If you don't have that, I mean, you might have to have that because that straight up equals this. So these equations are very similar. You just replace this Imax R with delta VR. All right, now that we have this, let's erase that and take a look at the equation with the capacitor over here. All right, so I'm gonna create a similar kind of circuit here, boom, with a capacitor, which has capacitance C. And remember here, V as a function of time still looks the same, V max times sine omega t. Okay, and we're gonna analyze the circuit the same way. We have delta V plus delta VC equals 0. Again, this could be a minus sign, could be a positive sign. It doesn't matter too much. I mean, it does matter, but for the purposes of this demonstration, don't stress about it too much. So after we have our setup right here, my main goal here was to derive this guy. But what we're going to do here is actually a little different because of the behavior of the capacitor. So take a look at the standard capacitor equation in the first equation sheet, and you will see Q is equal to C delta V, or delta V, the voltage across the capacitor, is Q over C. Cool. And also, if you remember, this is going to come in handy in a second, current is actually the change in charge over time. So if we take a derivative of this equation, then we can get dq dt is equal to d dt of C delta Vc. And this gives me the current. And this actually gives me this equation. So the current in a capacitor or across a capacitor is equal to the capacitance times the derivative of the voltage across the capacitor with respect to time. Okay, this is very different from the current across a resistor, which is from V equals IR, this over here. So now that we know this, we're going to analyze this equation here using Kirchhoff, the one we got using Kirchhoff loop rules. And like before, we're going to replace the voltage supply, which is straight up a V max times sine omega t. Let's do equals negative, and then I'm going to replace this Vc, which we said was Q over C. All right. Now, if I actually want to find an equation for the current on the capacitor, like we saw up here, we're going to have to take a derivative with respect to time. So whatever I do on one side, I do on the other. Here I have a derivative with respect to time of the left-hand side. And on the other side, I take a derivative with respect to Q, and I pull out this capacitance, 1 over capacitance. This is a constant. And the derivative of Q is I, and I'll put a C here. I'll also put I as a function of t, because the current is a function of time. Cool. Now I can expand this derivative here, and the Vmax is a constant, so I can pull this Vmax out of the derivative, and I have to take a derivative with respect to time of this sine function. So if you're a little bit uncomfortable with that, I would say just brush up on your derivatives of trig functions. Take a look at a YouTube video. But basically, the derivative of sine is cosine. And since we have another variable in here, we have to use the chain rule and take a derivative of what's inside the function we're differentiating. So that spits out an extra omega here. Now we can equate this to the other side. And now I have an equation for the the current going through the capacitor. I have this negative IC over here, which I will move to the other side. And that will give me negative omega C, right? I'm taking the C from here, moving it on this side. I'm grouping it up with this omega, and I'm moving both the omega and the C and the minus sign at the front of the equation. And then I'll just rewrite this stuff over here. So I have negative omega C times Vmax times cosine omega t. And this equation here is given to you in the equation sheet. Let me box it like this. So if you take a look in the equation sheet, we have, let me erase this. We have IC over here, current in the capacitor, omega C, Vmax, sine, and then this thing here. So there's a couple differences. We do have this omega C and this Vmax, except here we have a cosine, not a sine, and we don't have this pi over 2. And we're actually missing a minus sign over here. So if you take a look, we have I, the current as a function of time through the capacitor. We have omega c times V max, which is the same thing we see in the equation. And then we have minus cosine omega t, where in the equation sheet it was plus sine omega t plus pi over 2, if I'm not mistaken. Yeah, plus pi over 2 here. So this and the this can be converted to negative cosine omega t, and we will see that in a second. You can actually see it used over here. See how there's a negative cosine omega t, and this is the voltage on the capacitor. What we derived, though, was the current. So let's take a look at this very quickly, and very, very interesting. Now, if you take a look at this first section here, remember Ohm's law, V equals IR? So take a look at this. I'm going to write I, let's do I max, and just replace this C for a max. And then I'm going to do omega C V max. Now, if I want to get it in the form of Ohm's law, V equals IR, I'm actually going to move this entire thing here and divide it on this side. Are you guys okay with that? So if I divide that, then I get I max. Here I get 1 over omega c equals V max. Now this is very interesting. This is V equals IR. And this thing is the impedance of the capacitor. You can see it's 1 over omega c. This thing is straight up like the R, and actually it's defined as X subscript c. And you can see that in the equation sheet over here. So if you remember Ohm's law, you actually get to this stage. And if you take a look at this, so voltage drop across the capacitor, you can see it depends on this sine function, right? We will see why this sign over here has minus pi over 2, and the sign over here has plus pi over 2 when it's for the current. But just take a look at the first stuff over here. We have V equals IR, like the R in this case is this XC, and if you plug XC in, it's actually 1 over C omega, the capacitance times the frequency of the AC circuit. And this type of Ohm's law is the same thing as the resistor Ohm's law. You just replace the resistance with the quote-unquote resistance of the capacitor or the impedance, and they actually give that to you. And this thing is actually derived if you use Kirchhoff loop rules, and then you actually take a look at the current going through a capacitor. The current going through a capacitor is dependent on the time derivative or the change in the voltage. So that's an important thing to know, and you get to this equation here. No need to remember all of that. Just keep in mind Ohm's law. Keep in mind that the impedance of a capacitor is actually omega c. It depends on this, and it's also here, it depends on the frequency of the circuit, and it's in the denominator over here. So this thing here. And also, if you take a look at this equation, you can manipulate it around a little bit to get yourself to this equation. So we start from this one over here. Like I said before, this sine omega t pi over 2 can be converted into cosine. So you can see here I actually have the classic sine function in red over here and a negative cosine function. If I change the amplitude, they both change. So we'll leave that at 4 over there. Let's leave it exactly at 4. Damn. And you can see they're slightly out of phase. The tip over here for the cosine is at pi over 2, 4. And the tip over here for the sine is at pi over 4. And then the same thing, you can move on and take a look at the other ones. Now what I'm going to do here is actually add that little pi over 2 phase factor. Pi divided by 2. And take a look at this. If I add a minus sign onto the cosine function and add that little phase factor in the middle, it perfectly aligns with the sine function. You can see they're lying right on top of each other. If I remove this minus sign, then they're again out of phase. So you have to have the minus sign and the plus pi over 2. And basically, this is a way of converting from sine to cosine or from cosine to sine. They're the same function, they're just shifted a little bit. So now that we know that, we know how to get from this sine omega t plus pi over 2 to this negative cosine omega t plus 0. There's nothing else in here. So if you can convert that into the sine version over here, then you can get the current on a capacitor. And from there, you could just convert this over here using Ohm's law. So take a look at this. We have omega c V max. If you apply this equation, which is V max here, and over xc, you take xc, which is this, and it flips this c omega at the top, and you basically get this thing over here. Now you can replace that with I max, and you get to the current. So kind of a roundabout way of getting to this equation, but just keep in mind how we got there. We applied Kirchhoff's loop rules, and we applied the capacitor equation, which is this Q equals CV, which again was given to you here. Check it out, Q equals CV. Q is equal to C delta V max. And since we're in AC circuits, we have this extra sign factor. Okay, so now that you guys have that in mind, please take a look at the final circuit, which will be the inductor. So we have a voltage supply here, delta V, and we have the inductor here. We're going to apply Kirchhoff's loop rules the same way. So we have delta VL. Delta VL is the voltage drop across this capacitor. This is VL. And we're going to equate this to 0 because of Kirchhoff's first law. Now we can replace this delta V, the function that we're applying. It is literally delta V max sine omega t. Remember, this is what the engineer applies to the circuit. This function can always be different. You can apply a sine function, cosine function, square wave, like anything, except then the mathematics and like manipulation that we're doing here will slightly change. But if you can do it with the sine, you should be able to do it with other functions as well. I mean, at the end of the day, you don't have to do this on an exam. I'm just showing you where it comes from so you can kind of get a feel of what's going on. So in the capacitor equation, we took a look at what this was, which was Q is equal to C delta V, and we can get this delta V for the capacitor from this equation. Let's take a look at our equation sheet and see if we can find something similar for the inductor. Since we learned about the inductor fairly recently in this section, you'll see that we're going over this section here, right? We're taking a look at this equation over here now. We're trying to derive this for the inductor. We already took a look at the voltage for the resistor, for the capacitor, the current on the capacitor, and we saw how we can derive this guy. Now we're going to take a look at this equation here. And if you scroll up a little bit, you can actually see this section for Faraday's law has a section on inductance. And right in here, you can actually see epsilon subscript L is equal to negative L di dt. So derivative, and this epsilon L is the same thing as the drop in voltage on the capacitor. So keep in mind this equation. This is analogous to the capacitor equation, where the capacitor equation looked like this, is equal to Q over C. So I'm going to get back to that in a second, but we're going to use that equation into our Kirchhoff loop rule. So our Kirchhoff loop rule is right over here, and I'm going to rewrite that equation. So we have delta VL is equal to negative L, and here we have a derivative of the current with respect to time. Very important equation. Keep that in your brain for the time being. So we're going to do a minus sign here. Actually, since we have a minus sign here, and we're going to eventually move this on this side, I'm just going to do that right now, put an equal sign, and then just to remove the minus sign. So if you want, do this step by step, but we get to this stage over here. Now, what I'm trying to do, just like in the capacitor, you saw that at the end, I found the current for the capacitor, and from that, I was able to confirm this equation is true, and then build up to this equation. So if I have this, then I can just apply this I max is equal to V max, or like basically Ohm's law. From here to this equation, I can just use Ohm's law. Cool. So I'm going to do the same thing in this scenario, except I noticed that the current is now stuck inside of this time derivative. For the capacitor, the current was actually not stuck anywhere. We had to take a derivative in order to get the Q to turn into the current. That was from this equation here. Derivative of Q with respect to time gives you the current, and that was the actual current through the capacitor. In this case, we have the voltage across the capacitor is proportional to the derivative of the current through the capacitor. So for that reason, in order to get this I, we have to take an integral with respect to time. Then we can get rid of this, and we can get the total current through the inductor like that. If I take an integral on this side, I have to take an integral on this side. So that's how we're going to solve this equation. This L I can move on this side, and I will have di dt is equal to V max over L, and then we have sine omega t. Now I can also multiply this dt on this side. This is a separation of variables technique. So I'm left with this. Mathematicians don't really like doing this here, but for this class it should be okay. So whenever you see a dt and di, you may have seen these equations before with, remember the Biot-Savart law, the first video? So we could take an integral on both sides. On this side we get the total current as a function of time, and since we're only looking at a circuit with an inductor in it, this inductor here, then we can actually put an L over here. Okay, so in this scenario, we have a V max and an L. These guys don't depend on time. They are constant with respect to time, so we can pull them out of the integral. This gives us V max over L. And at this stage, we can now take an integral of sine omega t dt. So before we took a derivative of sine, we got cosine. Now we're taking an integral, and take a look at your integral and derivative calculus if you want. Again, for this class, it's not really needed. You should be fine without knowing this, but I'll just tell you guys, integral of sine is actually negative, so I'm going to put a negative sign here, cosine omega t. And from the chain rule, we also pop out a 1 over omega. With the derivative, we popped it out, the omega out in the numerator. With the integral, it goes in the denominator. So now I'm going to clean up this equation. I have IL as a function of time. I have a minus sign here. I have a V max. Now I have L omega, which also looks very familiar. And I have a cosine omega t. Cool. So keep an eye on this equation here. And let me bring in to play this equation sheet here, so we can just take a look at it a bit closer so we can analyze it. So what I derived here was the current as a function of time for the inductor. For the capacitor, we actually had that equation here, but I can't see it anywhere for the inductor. All I see is delta VL. And I can see here I have Imax X subscript L, Imax X subscript C. Very similar stuff compared to the capacitor. And here we have sine omega t plus pi over 2, sine omega t minus pi over 2. And here we actually have this cosine function, except there's no minus sign. So I think I made another mistake here with this minus sign. I'm just going to remove it. Like I said before, don't worry about these minus signs. Just get rid of them if they don't look good. Or at the end of the day, you could just say magnitude and be done with it. So we have V max over L omega, and that equals I. So take a look at this part and keep in mind Ohm's law again. This is very analogous to this equation over here. And also keep in mind that X subscript L is omega L. So if I take this whole thing, L omega, and multiply on this side, I get this equation. V max is equal to I subscript L, or you could say I max. When there's a V max, there's an I max. That's what these equations here are telling you. And we multiply this by L omega. And this L omega in the equation sheet actually is X subscript L. So the same way as how we derived the impedance here, or the reactance of the capacitor, we saw it was 1 over omega c, right? Because when we set it up in Ohm's law, we get 1 over omega c here next to the I, and we get V over here on this side. For the inductor, we get Ohm's law, V equals IR, and we get the resistance, or quote-unquote resistance, or the reactance of the inductor is L omega. And we also see that it has this cosine behavior here. So similarly, plug in cosine into a function like this, and you can see positive cosine can be converted into this sine omega t plus pi over 2. So this plus pi over 2 converts a sine to a cosine, and this minus pi over 2 in this sign converts it to a negative cosine. Okay, all of that to say that the equations over here in the equation sheet are basically voltages across circuits with this type of resistance. So this is the resistance of a capacitor, or the impedance or reactance. This is a standard resistor, and this is the resistance or impedance or reactance of a inductor. Very cool. Now I think we've covered most of the equations, and like I said, when we derived these guys using those Kirchhoff loop rules, again, keep those in mind. You most likely won't have to derive anything like this from exams, but it's good to know like where things come from and what things mean. But you saw when we derived these couple equations here and using Ohm's law, we actually came into notice that these things here were defined that way because these are kind of the resistances of the capacitor and inductor. So keep those in mind. Now I think we can finalize with these couple equations here by talking about the differences between all of these functions. So I'm going to quickly plot this sine omega t minus pi over 2, sine omega t, and sine omega t plus pi over 2. So here I have three functions. I have the red one, which is the standard amplitude. Again, we can move the amplitude up and down. Right now I'm going to leave it right there at 6. We have sine omega times x. In this case, x is the time axis, the horizontal axis, and y is the voltage. Or you could say the current. It really depends on like what you're plotting. But let's say it's the voltage, the standard voltage oscillating sine. Then over here, I have another function. This guy is the same amplitude, a, sine omega x plus this pi over 2. And you can see it's different from the other one. They're a little bit offset. And finally, I have the same function except minus pi over 2. So you can see all of them plotted together here. You could see the sine function without the little phase factor, the pi over 2, is just the standard sine. It starts at 0, increases, reaches a maximum, and then decreases. The one with the purple one, the one with the plus pi over 2, actually looks like a cosine. It starts at 1, or the maximum, which is amplitude 6, and then decays and goes to 0. And then the one with the minus pi over 2, the blue one, starts at the negative amplitude, -5, and then it decays down. So if you take a look at these waves and you compare them, you could see the red one is kind of in the middle. The purple one is delayed a little bit if you take a look at these peaks over here. So this peak for the purple one is slightly behind this peak for the red. And the peak for the red is also slightly behind the peak for the blue. So you can see each of them there and their phase factor, like where they are on the x-axis. So keeping that in mind, this is the behavior of capacitors and inductors. With the resistor, you connect a resistor to a voltage supply, and the current in the resistor or the voltage in the resistor is in phase. It follows the same function that the resistor follows. But for the capacitor and the inductor, they're slightly offset, and the way their behavior works is they're offset by this phase angle, pi over 2. So that is why you see these different sine values over here, this one, and this one for the inductor, resistor, and capacitor. You can see the resistor doesn't have that phase angle. It follows the same function that the voltage follows. The voltage was, for example, this function. I'm kind of pulling it out from this Q equals CV equation, but imagine just this thing here. This is the voltage as a function of time applied to the resistor. If we apply that voltage to a conductor, or sorry, a capacitor, the capacitor is slightly ahead because of this minus pi over 2. When you have a minus pi over 2, it's ahead. So that's this blue one over here. You see how it's minus and it's slightly ahead of the red one? But when you have a plus pi over 2, it's slightly behind. You see how it's slightly behind the red one? So keep that in mind. And the reason this is happening is because the current inside a resistor is proportional to the voltage. So we have 1 over R, V equals IR, and then we have V as a function of time here. However, the current in a conductor is, do we have that actually? Well, let me bring up the actual equation, because this one for the resistor is straight up Ohm's law. What we saw on the inductor was the voltage as a function, I'll put a little R here too, as a function of time is equal to negative L di dt. So the current is actually buried inside this time derivative, and the voltage depends on the change in the current. That's why it responds a little differently than the resistor. And then we can also take a look at the voltage on the capacitor, which looks like this: Q equals CV. So it would be Q over C. And if you remember this, if you take a derivative of that, you get a current over C. And actually, let me write that equation over here. So you get the derivative of the voltage on the capacitor with respect to time. And that gives you, actually, if you multiply this whole thing by C, this gives you the current on the capacitor as a function of time. So keep in mind these equations, and this is what we got from Q equals to CV, and this we got from the first equation sheet in that inductance section. So the resistor responds to the voltage and the current in like a linear relationship, but the inductor and the capacitor, they have these derivatives inside of them. You see the derivative with respect to the voltage. That means the current depends on how fast the voltage is changing. If the voltage is not changing, there will be no current. If, in this case, the voltage of the inductor, the current is not changing, then there will be no voltage. And all these things intertwine. Like, you can cancel this derivative with an integral. So you could get like the current here for the inductor is like proportional to the integral of the voltage with respect to time. So the inductor depends on this integration behavior of the voltage. That's where you get the current from. And the current of the capacitor depends on this derivative of the voltage. So they're both interconnected with these integrals and derivatives. And that's why you get these behaviors of these oscillating like sine functions and stuff. So the whole thing that I just shared with you guys was a summary to show you how a oscillating voltage source with Vmax and this behavior where it oscillates as a sine wave, this gray curve, it will produce different effects on the voltage or current or whatever, Ohm's law interchanges the two on different devices. So if you connect it to a resistor, the amplitude will be this VR, whatever the current and the resistance is through this resistor. And the resistor will actually have the same waveform as the sine function. So you can see the resistor here rises and drops, and it reaches a maximum value the same place that the voltage source reaches a maximum value. So these guys are in phase, and they reach 0 at the same place. You see the red and the gray. They reach a minimum in the same place and 0 in the same place. Maximum in the same place, 0 in the same place. Minimum in the same place, and so on and so forth. The capacitor actually is ahead a little bit. A minus sign here means that the sine function is shifted a little bit to the positive side. And you can see that as well here. So wherever this thing reaches a maximum, the voltage on the capacitor, the actual supply of the voltage is at a 0. You see that? And whenever this thing reaches a 0, the voltage on the capacitor, the voltage supplied actually reaches a minimum. And they oscillate like this, they dance and like interchange themselves. And the inductor is a little bit different still. It's still a sine function, VL you can find with that impedance equation there, but there's a plus pi over 2, which pulls this thing backwards to the negative t side a little bit. And here it starts at a maximum where the voltage supply starts at 0. So already it's at a maximum voltage, and then it drops, reaches a minimum value here of 0 where the voltage is at a max. And then it reaches its maximum negative side here where the voltage supply is 0. And they keep dancing like this. So this, I drew it off a little bit to the side. This should actually have been over here to line up with the max here. But basically, you can keep in mind that all these guys are slightly different. The capacitor and inductor are out of phase from the original voltage supply. So keeping that in mind, you can actually track this behavior using vectors. So you could see where this vector is compared to this vector, compared to this vector, and the distance they differ over here. This will be the phase angle. So you can see how this pi over 2 is actually a phase angle compared to this 0. If you've learned anything about the unit circle, you can actually plot these guys here on something called the real and imaginary plane. No need to worry about that, but basically if you have a circle here, you can start over here at 0 degrees or 0 radians. Over here at the top, you reach 90 degrees or pi over 2 radians. Over here, you reach 180 degrees or pi radians. Over here, it is 270 degrees, or I think it is 3 pi over 4 radians, if I'm not mistaken. Hold up a second. No. It's 2 pi. Okay, I'm not actually sure which one that is, but here, when you go all the way around, it's 2 pi radians. So radians and degrees, it's a way to interchange them. Let me actually think about this. So here we have 2 pi, here we have pi. Here it's pi over 2. So from 0, you add pi over 2 here, then you add another pi over 2, then you add another pi over 2. So pi plus pi over 2 equals, if we put these under common denominator, it is 3 pi over 2. Yeah, I think that looks good, because this is 0 pi over 2. This is 1 pi over 2. This is 2 pi over 2, which is the same as pi. So this would be 3 pi over 2. And this would be 4 pi over 2, which is the same as 2 pi. Okay, that makes sense. So I made a slight mistake there. This is 3 pi over 2 radians. So you can actually plot these phase differences on a graph like this called a phasor diagram. So typically you can plot this resistance one over here. The resistance is at 0 because it doesn't have a phase angle over here. It's plus 0. It's in the same phase as the voltage, right? If the voltage was somewhere here, then you would also put the resistance vector there. Might be a little bit weird, but for now, let's just plot this as like the R vector. And let's take a look at where we would plot the other ones. So you can see here actually, VC is minus pi over 2. So looking at our thing here, plus pi over 2 goes this way, minus pi over 2 would go this way. So I can actually take this blue and plot another guy here. I will call this XC. And then I can take a look at, that's the minus pi over 2. For the VL, we have a plus pi over 2, and that means we can go this way to plot in orange this plus XL. And this phasor diagram is telling you a couple things. First of all, the resistance here is at a phase angle of 0, meaning it is completely in line or in phase with the voltage source. The inductor is pi over 2 radians or 90 degrees ahead of the resistance. And you can see that here where there's a plus pi over 2 phase. So this is the additional phase factor. That's what makes it different from the resistance. And you can also see it here. These guys are 90 degrees apart. This this vector here is 90 degrees ahead of this vector if we're tracking ahead this way, starting from here going this way. Meanwhile, this guy, you can say it's 270 degrees ahead of the resistance, but you can also say it is 90 degrees behind, because if it is 270 ahead, remember that these functions, if you take one and you shift it a little that way, it can align again with another one. So they're repeating functions. So yes, you can say it is ahead by 270 degrees. The XC is ahead of the R by 270 degrees. Or you could say it's lagging by pi over 2 or 90 degrees. So those two things are good to keep in mind. And that's also something you get from over here, this minus pi over 2. Now, if you take a look at this and keep in mind the vector video that I posted, you can actually break apart the total impedance by adding up little vectors here. So you could see this vector and this vector are both in this y-axis. You can combine this guy and this guy by doing minus xc here and adding it to this. So you get xl minus xc. And you actually see this in this equation over here, xl minus xc, and over here xl minus xc. That's another, and xl and xc are given to you here in terms of the inductor value and the frequency of your AC source, and the xc is given to you in terms of the capacitance value and the omega, the frequency of the source. So if you take a look at this and this, you can see these things xl minus xc, and this is where it comes from. These guys are normally completely out of phase. I mean, they could be made to go slightly in phase depending on the frequency and stuff. But here, you can add these vectors together. So I'm going to do this vector diagram here where we have one vector like this. I will call this xl minus xc, right? And we have another vector here, which is just r. If we find this side, this is c squared is equal to r squared plus xl minus xc squared. This is just Pythagorean's theorem. We could take a square root of this whole thing and we can get the length of this side, which we will actually call z. And this is the total impedance, or it's the total resistance of the circuit that has an inductor in it, a capacitor in it, and a resistor in it. Now, keep in mind, if your resistor is 0, then you have 0 plus this thing squared. This square root removes this squared, and the total impedance becomes xl minus xc. If you instead had 0 of this, then you have 0 minus this, you get negative this. You square that, it becomes this squared, and this minus sign disappears. You can add it with this, and then you get the same thing, a triangle where one side is just xc and one side is r, and you find the total impedance z over here. If r is equal to 0 and you have no capacitance and you have just an inductor, this is equal to 0, this is equal to 0. So the whole impedance here just becomes xl. So whatever your circuit has, this is a way of tracking all of the resistances all at the same time, and that's why it's included here in the top of the equation. So the total impedance of the circuit depends on the resistance, and it also depends on the capacitor and the inductor, and it depends on this way. And this minus sign is because of this leading and lagging behavior which the functions display. And that also all comes from the equations we had here. So the voltage on the inductor depends on the change in the current, and the voltage on the capacitor depends on the charge. So the current, which depends on the change of the charge, depends on the change of the voltage. So all of these changing behaviors and stuff, it leads into this phasor diagram, which is an easier way of tracking all these weird phase changes and stuff here. So yeah, that is where this equation comes from. Now let's take a look at, so we've handled this equation too. Let's take a look at this equation. Take a look at my vector video and you'll see that this equation here, I talk about it a little bit. Basically, it's tangent inverse. And here you have this xl minus xc. And on the bottom, you have r. Is that correct? Let me double check. Tangent inverse. So this is the phase angle. You can see actually, if you remember SOHCAHTOA, which is in that vector video, make sure to take a look at that if you need some help with vectors. SOHCAHTOA, this here is tangent, meaning this thing over here is the opposite side, and this thing over here is the adjacent side. So if we have an angle over here, This side over here is the adjacent side, and this side over here is the opposite side. So this equation is a way of getting the angle between this vector here, this r, and the addition of these two vectors. It's the phase angle. It's the angle of basically the total impedance here. Yeah, maybe there's a bit more stuff to talk about here, but for now, I just want you guys to keep that in mind. And if you want to find the phase angle, you set up this triangle here. You find the total addition of the XL and XC reactance impedance components. You find R. You could set up this triangle here and find the phase angle. So this here is phase angle. And you can find it using this thing, which is basically, it goes back to triangles, trigonometry, and vectors, and this stuff here, which I talked about in the vector video. So take a look at that. So in big summary, this thing over here comes from plotting the voltages, currents, and reactances on a phasor diagram. Where we got those differences from, well, they are the components here, these guys are actually given to you over here. And where we developed these guys from is by analyzing different circuits and how they respond with different components like a resistor, capacitor, inductor, how they respond to different voltage sources. One final equation over here is this guy over here. And this is basically telling you, again, take a look at the conductor video. If you have, or sorry, the vector video, if you have the total impedance, which is this Z over here, and you want to find just the resistance component of it, you take cosine of 0 and you multiply that by Z. So why does that work? Well, if you move this Z over here, you have R over Z is equal to cosine, in this case, theta. And if you remember, cosine of theta is equal to so katoa, so it's adjacent over hypotenuse. So what we get here is R over Z. So this is the hypotenuse, and this is the adjacent side. And you can actually see that here. This is Pythagorean's theorem, a squared plus b squared equals c, and then you take the square root to remove the squared. And if you see it over here, we have a squared plus b squared, it gives you c squared. And this angle over here, you can do cosine. So cosine of this angle here, it's either theta or phi or whatever. Cosine is adjacent over hypotenuse. So if you have this angle, you can find the resistance or the total impedance. Again, the vector video goes a little bit more deep into how to work with these vectors, so I think it's pretty useful. But it's good to get a big overview of what this stuff is talking about. So I know this video is very long, guys. I think I'm going to cut it off here. Let's take a look at just the big equation sheet overview very quickly. Yeah, these kinematic stuff, oh man. So if you want to find a final velocity and you have an initial velocity, you have an acceleration, and you have a time at which the acceleration has taken place, multiply acceleration by time, add that to the initial velocity, you get the final velocity. Same thing with final distance. If you have you want to find how far your object has moved, and you know its initial starting point, you know its initial velocity, you know how long it traveled at that initial velocity, and you know the acceleration that it exhibited. If it exhibits 0 acceleration, then you can plug in a equals 0 and this whole term cancels. But you can find the total displacement of an object if you have those things. If you want to find the final velocity, you can also have this equation with the velocity squared. Again, acceleration here. If acceleration is equal to 0, then the velocity just stays the same at the start and at the end. Here you have another displacement equation, the final location of an object, the initial location of an object. Here, if you have the final and initial velocities, you can add them up and take like an average and multiply by the time that which your object is moving through space, and you can find the displacement of the object. And these equations here are all identical to these ones, except just change the scenario. Here, everything is linear, and here everything is angular. So here's an angular displacement with which is different from linear displacement. Angular velocity, angular acceleration, all of that. So big overview of this thing. We went over this equation, this, and then we went over some physical constants and these. We went over most of these equations. These two equations here I didn't go over. Take a look at some LC circuit videos, and we ended off with this equation here. If you want to find the frequency over here, For just LC circuits, you have this frequency here. But once you get to AC circuits, your actual voltage source has a oscillating frequency. And to end off, I want to show you guys just a couple more videos I found kind of useful. Take a look at this video here by Charles Clayton, some video I found introducing phasors, impedance, and AC circuits. They actually talk a little bit more about this real and imaginary axis. This is a little bit more complicated. We enter like imaginary complex numbers. Not too important to know this. It's a little bit more advanced if you want to study circuitry at a more advanced level. For this class, you just need to know the behavior is different and those little sine functions and stuff like that. Also, take a look at this video. This guy solves some RLC circuits, this Michael Van Biesen. He has a lot of physics videos. Just search up some RLC circuit videos and take a look at this. I like this video and some others because they use this mnemonic, Eli the Iceman. So this is a way of remembering which one comes first. I think current is ahead of the voltage if you have an inductive circuit with an L, but current is behind the voltage if you have a capacitive circuit. So let's see if that's true actually by taking a look at my little stuff here. Oh man, these are all voltages, but I think maybe it should work. So voltage for a capacitor is actually ahead of the voltage here, and voltage of the inductor is actually behind. So voltage of inductor is behind. Let me see if that's the same here. Voltage of inductor is behind, yeah, and voltage of the capacitor is ahead. Okay, I don't know if that's true, but take a look at these two videos. I think they're very useful. And also take a look at some of my other videos if you need some refreshment. This is the first half of the semester. Take a look at this stuff as well. This is the second half. I know this is a lot of content, but guys, you learned pretty much all of electromagnetism in one semester here. I would like to talk about Maxwell's equations because normally electromagnetism is like governed by these four Maxwell equations. Every like lover of physics wants to learn about these. And in this course, you didn't actually look at them too much, but you'll see that all of the stuff you learned here actually is built up from Maxwell's equations. So maybe I'll do a video about that a bit later, but for now, I'm sorry I'm releasing this like a day before your final exam. Good luck. Keep grinding on your other exams, and thank you all for watching. I will see you guys later.